A customer sent a jacket back last week. It reached the warehouse on Monday. Today, she asks the support assistant, "When will my money be back in my account?" The answer comes back. It is confident, it is clearly written, and it is wrong. It tells her that when an order is cancelled before shipping, the money returns to her account automatically. She did not cancel anything. She returned it after it was delivered. That looks like hallucination. But look at the policy. It was not invented. It came straight from the company's own help page. It is the correct answer to a question nobody asked. Nothing crashed here. Every part of this system did exactly what it was configured to do. It answered from the text it was handed. So changing the model or rewriting the prompt would not fix the retrieval mistake that started this. The mistake began earlier. Between her question and the reply, a search ran and chose which paragraphs the model would be allowed to see. That search did not read her question the way you just did. It did not work out that a delivered item had come back. It scored them. It turned her words into something it could compare against the paragraphs it had, and it took the highest scoring candidates it found. The part that writes the answer, the generator, only gets involved afterwards, reasoning over material that retrieval has already selected for it. This design has a name: Retrieval Augmented Generation, RAG. Before the model answers, another part of the system fetches outside information and hands it over as context. So there are two jobs here. Choose what the model gets to see, then generate an answer from what it saw. This video is mostly about the first one because that is where her wrong answer began, and there is no single way to build it. What follows is one common design. Split the source, turn the pieces into positions, retrieve a shortlist, then hand that context to the model. Other designs split the text differently. Some do not split it at all. In the pipeline we are following, the documents get split. A chunk is one piece of text that is stored and retrieved as a unit. That is the whole definition. Not a paragraph, not an idea, not a topic. Whatever the splitter decided to cut. The splitter cuts before anybody has asked anything. Watch what that can cost. Here is the refund page. Returned items are inspected once they reach the warehouse. When the return is approved, the refund is issued. And after that, the bank may take longer still to post the credit. Cut between those last two sentences, and one chunk knows when the refund is sent, and another knows why the money has not arrived yet. Her question needs both. Each chunk holds half of the answer, and each one looks complete on its own. Next, every chunk gets turned into numbers. An embedding is a list of numbers that represents a piece of text as a position. Once every chunk is a position, her question becomes one too. One more point, dropped in among the help pages. Comparing them becomes arithmetic, and the retriever uses those positions to search for the highest scoring chunks. But a similarity score is not the same question as, does this passage answer the person who asked? A vector space is the coordinate system those positions live in. The real one has far more directions than a screen can show. So this is a flattened picture of it. Text used in similar ways lands in similar places. And that is genuinely powerful. It is why a question about getting money back can reach a page that never uses those words. Now, look at these two. One says the refund is issued once the returned item has been inspected and approved. The other says money returns to your account when an order is cancelled before shipping. Related subject, related language, different business state. In the illustration, they land close together. Near doesn't mean answers this question. A representation may encode that distinction. For a particular query, it may not separate the two enough to change their order. So retrieval takes the nearest. How many is the nearest? You decide that in advance, and it is called top K, say 5. Only those 5 move forward. The rest are still sitting in your database. They are simply absent from everything that happens next, and the model will never know they existed. And the cutoff is drawn by that score, not by a separate check that each passage actually answers the question. In the example on screen, the chunk about the bank posting the credit misses the cut. 5 others travel onto the model, and in this one pass pipeline, nothing downstream can go back for it. Raise K, and you bring in more text, which raises the chance of catching what you needed, and also hands the model more context that may be irrelevant. There is no single K that is best for every question. The chunks that survived get pasted into a prompt above the customer's question and sent to the model. In this pipeline, one pass, no tools, the model cannot go and look anything up. It does not have your documents. It never sees the chunks that lost. It can notice that some of what it was given looks unhelpful. What it cannot do here is go and get the chunks retrieval never handed it. The model generates its answer from that context. And if the selection is wrong, it can still produce a fluent answer grounded in the wrong material. So go back to the words she actually used: money, back, account. Those line up strongly with the cancellation page. The refund page is written in a different vocabulary: returned, inspected, approved, issued, posted. It is describing her situation and barely sounds like her question. But the application already knew which order she meant. It knew the jacket was delivered, that it had come back, and that the warehouse had received it on Monday. All of that was already in the order state, and none of it went into retrieval. This drawing shows you the shape of that. It is an illustration, not a measurement. One obvious lever is the splitter. The developer tries bigger chunks, so a rule and its conditions stay together. Bigger chunks can preserve more surrounding context, and each retrieved unit now covers more ground. So the developer tries the opposite. Smaller chunks can be more specific, and information that belongs together is easier to separate. Same documents, same questions, same model, only the split moved. There is no size that wins everywhere because the useful granularity can depend on the question and on the document. That is where structure aware approaches can help. Keeping sections whole, overlapping the edges, or storing a small piece that knows which larger piece it came from. Even when retrieval works, there is one more failure point, and it is not in retrieval at all. Suppose the right chunk is found. It is in the prompt. Everything we have looked at so far did its job. You are still not finished. Where that chunk sits inside the prompt can matter. Research on long contexts found that models tend to use information near the beginning or the end more reliably than information sitting in the middle. This is often called lost in the middle. So once the context you are handing over is long enough, the same evidence in a different position may produce a different answer. This is not a law. It showed up in long context settings, models differ, and it may not appear in what you are building. But it means retrieval can return the right passage, and the model can still fail to use it. So what helps? Not one fix. This video has shown several different failures, and they have different answers. When the state your application holds changes the meaning of the question, you can carry that state into retrieval in the query itself or through metadata and filtering. For exact terms, product codes, error codes, names, lexical search gives a literal word match a direct signal. So a common design combines lexical and semantic retrieval. And when the first ranking is weak, poll a wider set of candidates, then re-rank them. Score each one against the question using a slower model that reads the pair together, and keep the best few. That is a different stage doing a different job, not another comparison of positions. None of this guarantees a correct answer. Every fix has a boundary. A re-ranker cannot rescue evidence that never reached its candidate set. Enriching the query cannot repair a bad split. And if the pieces you need never survive together into the context, the generator cannot use evidence it was never given. So ask her question again. This time, the query carries what the application already knew. This order delivered, returned, received at the warehouse on Monday. Retrieval pulls a wider set of candidates. A re-ranker then compares each of them against the enriched question. In our replay, the refund page moves to the top. The generator's context now holds the chain. Her question actually depends on the warehouse receipt, the inspection, the approval, the refund, and the bank posting the credit afterwards. That does not make the system reliable. In this replay, the missing state finally reaches retrieval, and the re-ranker gets a better set of candidates to judge. The next question can still fail somewhere else, but now you know what to test. What entered the query, what made the candidate set, how it was re-ranked, and what context reached the generator. RAG does not hand a model your knowledge, it hands the model a selection. In the pipeline we followed, that selection was shaped by how the source was split, what reached the retrieval query, how the candidates were scored, how many of them moved forward, and where they landed in the context. Different systems make those choices differently. The habit is the same. When the answer comes back wrong, inspect what actually reached the model before you change the model. If you like seeing how systems actually work, subscribe. That's what Code Seeker does.